Hey guys, David here and welcome back to the series where I show you how you can build your own custom keyboards. In this video we're going to talk about how to integrate the controller onto your custom PCBs. That way you can have a much cleaner look without an Arduino glued to the back. And we're also going to talk about integrating USB-C ports so you have the most modern connectivity and adding some more LEDs, custom stuff like that. So make sure to stay tuned. Before we get started, I want to give a big thanks to PCBWay for sponsoring this series, as they make super high quality PCBs for a very affordable price. You can get up to 10 pieces, 10 by 10 centimeters, double-sided, silk screen, everything. For example, like this keyboard PCB for just $5. And if you use my link down below, you get $5 off your first order, meaning it's free. All you have to do is pay shipping. They're also celebrating their 8th anniversary right now, so make sure to go check out the website linked down below for any more deal info. In the last video of this series we built this cute little keyboard with an Arduino on it, and I used this to explain how the basic concepts behind DIY keyboards work, like the switch matrix, how to connect all of that up, things like that. If you haven't seen this video, make sure to go check it out. Pause this video, go watch this, and then come back, as I will not explain these concepts again. And it will be kind of hard to understand it if you don't know how it works. Now, the basic concept behind what we're doing now is essentially we're taking all the components that are on the Arduino Pro Micro and we're integrating them into our own circuit. This does mean a couple of things though. For one, we have to source all of these components. We also have to make sure that we integrate them properly so everything works. But finally, it also means that we can customize everything to our heart's content. We can integrate more things that we want, like for example, we can integrate a USB-C port instead of that crappy micro B that is on the Arduino, and we can leave out stuff that we don't need. Once you've gotten the hang of and you kind of know how these microchips work, that are actually really easy to integrate since they have most of the logic already on the chip. It's really straightforward to build cool PCBs like this one that don't have any extra flash hanging off the side and look like professionally made. For this revision I also went ahead and integrated some LEDs on the back. That means that you can have them shine through the case and have everything nice and glowing, and they're all integrated in the same ecosystem, so any effects will go all around, which should make it look even more cool. But as you might be able to imagine, having all of that functionality on the PCB makes it a lot more complicated, and there's quite a bit of components on here. So how about we jump over to the computer and I'll show you that in more detail. Alright, here you can see the finished PCB inside of Eagle. As I've mentioned in the last video, I'm using Eagle, but you can just as well use KiCad or any other PCB design software that you like. It's just the one that I'm the most familiar with, and it works for what I'm doing here. Now, minus the ground ports that I have not enabled right now to be able to see the traces a bit more clearly, this is how the finished PCB looks. Up here you can see the USB port. It is mostly a surface mount here with these pins, and just some shielding is with through holes. I quite like this design. There are like dozens and dozens of different USB-C ports available, but this is the one I've chosen, and it's quite nice. You can see all the pins in the back, and you can come back in with a soldering iron to touch up anything if there's any bridging or something, and there's nothing really occluded underneath it. It is also relatively small compared to some of the other ports that I've used in the past. Then down here is the main event. This is the ATmega32U4 microprocessor, and this is actually the MU footprint. Now, I would much rather use the AU footprint, which is quite a bit larger, but has the legs coming out, which just makes it a lot easier to solder and to diagnose any kind of problems. But if you do not have any spaces in your keyboard with these switches and the standard spacing, it is not possible to fit the AU footprint in between them. Now, if you are building a keyboard where you, for example, have a spacebar that allows for a bunch of space next to it, then you can definitely go with the AU footprint, and I would definitely also recommend that if you have the chance. But the MU also works, and it is possible to solder it, though I've had a lot more issues with this one compared to the MU. You also have a big ground pad in the middle, which means that you cannot route any vias down through the middle, which you can do on the AU. apart from that, the switches themselves should already look familiar to you. It's the exact same footprint as I've used in the last video, with the SK60L12 Mini E LEDs here that have a cutout in the PCB and the pads on the side, which are very easily solderable by hand or by reflow soldering. That's why I love this so much, and they work just great. I also do have a 6-pin header up here, which is to program the microcontroller. Now, it's not strictly necessary to add this, you can also just add some contact points, but it makes it a lot easier if you have a header. You can see this in the end as you have some holes, but I'm actually not soldering on a header, I'm just kind of pressing into place while programming. But if you want a more clean look, you can definitely also just do test pads. These footprints here are for the LEDs on the back, and I'm using some WS2812 LEDs here, and this is the 3535 footprint, which is the smaller ones, and they are a royal pain to solder. I've had so many issues with them, but it is possible to solder them, and you really can't fit the 50/50 ones on this PCB unless you make it bigger. And if you would use the same SK6812s, you would have to solder them from the other side, which would mean that you need to solder on two sides, which I really do not want. So I'm going with these ones, although I'm really not much of a fan, to be honest. You also do want to make sure that you have the pin assignments right for these ones, as the pin out is actually different for the 3535 compared to the 50/50s, which I don't know why they're doing that, but it's really confusing. I've made mistakes this way before. For example, like the little triangle or the notch on the LED for the 50/50s is where the ground pin is. Same for the SK60L12s is with the ground pin, but on the 3535 ones, it's actually with the data in pin. Still, just make sure you have the footprint right, and double check the listings that you are copying the footprint from, that they are actually for the 3535 and not for the 50/50, as those are much more common. Before we do that though, I want to take a quick look here at the datasheet for the ATmega32U4, and as you can see, it's 400 pages long. You do not read this. I have not read this. It goes over every little detail that you could ever want, but the main important thing to have a look at is the pin out here. And this is the same for both of the footprints, and you can see a couple of cool things. For example, here we have the data plus, data minus. This is where the USB port connects. And the reason why I like this chip so much, you do not need a separate USB controller. It just directly goes through a 22 ohm resistor into this chip. Then here you have a bunch of the pins, all of the I/O pins. There's a lot of them. Down here is where you have the crystal that you need to hook up, just a 16 megahertz crystal with some loading capacitors. There's also a reset, and there's other things, but generally this is a very easy chip to get running. You just need some decoupling capacitors, a crystal, and that's basically it. You might want to hook up like the programming pins, and of course your I/O pins that you want to control stuff with, but the only really things you need is that. Now, you do not need to come up with the circuit for this completely yourself. Since the Arduino boards are all open source, you can very easily just find circuit diagrams for them. This is one for the Arduino Pro Micro. I don't think it's the official one, but it was a higher resolution than the other one I found, and it looks very similar. This is basically where I got all my component values from, as I was way too lazy to read through the proper data sheet and figure out how big the decoupling capacitors and everything should be. So I just basically copied the Arduino Pro Micro, which is what I was using before anyhow, and left out the 3 volt step-down conversion, since I'm using just 5 volts for everything. And as you can see here, if you close this pin for 5 volts, then basically this entire circuit is bypassed. So I just ignored this. Here on the input, you have a 500 milliamp fuse, which is because the USB 2.0 specification allows for 500 milliamps at most. So unless you are using USB 3.0, at which point you do need to communicate that with the computer, you cannot use more than 500 milliamps, but that is plenty even with backlight. You really don't need any more. Then down here is for the USB input. It's very simple. Just have the power from the USB going directly into this fuse. Ground connected to ground. I also just connected the shielding to ground. And for the data plus and data minus pins, you just want a 22 ohm resistor in series and then connect them up directly to the microprocessor. You could not get any more easier than that. For decoupling, there is a UCAP pin that needs a 1 microfarad capacitors, and otherwise for all of the other like VCC pins, I have a bunch of 100 nanofarad capacitors just to make sure that it is nicely decoupled. The crystal circuit you can see down here, you have just a regular 16 megahertz crystal connected up to the two pins, and obviously you need also the loading capacitors. The datasheet says 12 to 22 picofarads. Since the Arduino Pro Micro is using 22 picofarads, that's what I'm using as well. And you just have those directly next to the crystal, and they really do need to be very close physically as well. Same with the decoupling capacitors, you should have those as close as possible to your microcontroller itself. Here you can see my circuit, and it is, as you can see, basically the same. Here are all the switches. You should recognize this from the previous video. This is the custom footprint from the library that I provided, linked down below, and it has the LED here integrated, the switch up here, and then you have the diodes here that make sure that there's no ghosting. If you're not familiar with this, go watch the last video. I explained this in very much detail. And down here I have all of the LEDs for the backlighting on the back, just connected in a series for the data pins with the key switch backlight. This is just a generic footprint I found for these LEDs. This is how I have the USB port hooked up. As you can see, I have essentially just the pins for the USB 2.0 specification hooked up, so data plus minus both of them, since USB-C is reversible, you do need to hook up both of them. On some footprints they are already connected, but on this one you just need to make sure to connect them, that way it actually works both sides, otherwise it will just work on one side. Here you can also see the pin header. It's very simple pin header and is connected directly to the respective pins on the Arduino Pro Micro. Now, if you are using these pins later for your keyboard matrix as well, that is no problem whatsoever. You only need these pins for programming, and then the chip will go into programming mode. So you can easily reuse these I/O pins for programming as well as for your key switch matrix. But since I'm just building a really small one, I have plenty of pins available, so I'm just using some of the other ones. Pin F7 is traditionally used for the LED, but realistically you can use any one of them. But that is just the one that is used in the software by default, so that's what I use. And once again, you have the 360 ohm resistor here. Anything in that neighborhood should work fine for the LEDs. Here I have all of the decoupling capacitors. This big electrolytic one here is mainly for the LEDs. It's 10 microfarad, but I don't know why it's not labeled here. That is just to make sure that when the LEDs are switching on and off, it does not cause any voltage dips for the microprocessor, as if you were to turn all of them on at the same time, it might cost as much of a voltage dip if the USB, maybe you're using some extensions or whatnot, that the processor might not like that as much. So you want to have a fairly large electrolytic one for that. The other ones are just the 100 nanofarad ones for the chip decoupling. And here is the 1 microfarad one for UCAP. As you can see, it really is not all that difficult. There's not that much to it. Once you kind of know how to do it, really, it's just a bit more risk, since if it does not work, you don't really have a way of knowing what exactly is not working. It's not like an Arduino where you can plug in with a USB and it already has a bootloader on it. If you buy these chips and you plug them in by USB, nothing happens, since you first need to add a bootloader. That is also why we need this programming pin, since we cannot upload anything over USB until we have uploaded something to the chip. Now coming back here to this PCB, I want to just give you some little tips and tricks for PCB routing for slightly more complicated designs like this. Now I do want to preface this by I'm not a PCB expert, and while I'm studying electrical engineering, we have not looked at any of this so far. It's been all theory. So this is just basically what I found that works and a couple of videos I watched. But if you want some more proper like best practices videos, go watch somebody else. I'm not the person for that. I'm just showing what works for me and what I've kind of heard on the interwebs. Now I've already mentioned that you want your decoupling capacitors close to your chip, and that is just so that you don't have any extra capacitances. So here they are all relatively close. Now of course you need to have them far away so you can route comfortably to all of the other pins, but generally as close as possible. Here for the crystal, just make sure that the two loading capacitors are close to it, but at the same time you don't want to like put these chips too close together. Like I wouldn't want to put this right here, as this basically makes this board not assemblable. As you do want to have enough space that you can get your tweezers in between to properly place these components and to reflow them without everything breaking. You can also see that the crystal here comes with 4 pins actually, although in the schematic there were only 2. And that's these 2 diagonal ones here are the ones that are connected to the controller, and then you just have ground here, which is quite nice, as you can have the capacitor, ground, and pin here right as well, which allows you to directly connect it and have everything be nice and neat. Now what I've found on my last PCB, and I don't know the full explanation for it, is that I believe if the crystal is too close to one of these LEDs, then it can mess with their circuitry, and I had one of them completely act up and like be completely unusable, where I had the crystal too close, like instead of down here, I had it somewhere up here, a lot closer to it, and that meant that I could not use that LED. So, but putting it down here has fixed that issue for me. Now I'm not sure if that was the issue, but since moving it down fixed it, I'm assuming so as much. On the topic of kind of interference, although you can place traces quite close to each other, like these ones for example, here I could place them as close as this together and they will still be within the minimum specifications for PCBWay. But if I have the space, I want to have them as far away from each other as possible. Now these are still relatively close to each other. If I had the space, I would space them out more. But for the kind of things that we do here, these kind of things does not matter as much. For the most part, if it's connected, it will work. We are not working with super tight timings, or also not with super high frequencies, so it should be fine. Same for the USB port. Technically, this is the differential signal with the data plus and minus, so you would want those traces to be matched and all the same length so that everything is perfect. But we're using USB 2.0, which is quite loose in timings anyhow, so as long as they're roughly the same length and you don't have one directly connected and the other one circling 3 times around your PCBWay, you should be fine. Other than that, you can see that I'm using 2 different trace widths. One is just a relatively small one that is just barely above the minimum for all of the signal wires, since there's not really a need for them to be any bigger, and this just allows me to have them more properly spaced. But for the power ones, I am using a thicker one, so all the VCC and ground lines are with a slightly thicker trace to make sure that they can carry the current without getting warm. Another thing that I added on this PCB are some holes to be able to mount it, and the way I did this was just to use a really big via. Now, I'm not sure if this is the right way to do it, but I essentially just made a 3.2mm via for some M3 bolts. This means that even with the plating on the inside, which will be deducted from your diameter, it still is big enough, and it allows also for proper grounding. Now I'm using a plastic case, so that doesn't matter, but if I was using a metal case this way, it would also automatically be connected to ground. But once again, I'm not sure if that's the proper way to do it, but it does work and it looks quite nice as well. Another tip for just some more clean PCBs is if you go to the properties of your silk screen, In a lot of cases, directly from the library, it will be very different. Like you will have different font sizes, different font weights. So what I like to do is, I think I've fixed it for the things in this library that I provide for you, but I like to set them all to the same font. So you can either have vector, which is kind of the default PCB font, and then the ratio is basically the thickness. So I like to set it to vector 10% and 0.8 millimeter size. That is very small, but I like small size screen, so it's just large enough so you can read it if you need to, but it's not bothers more in the way. You can go larger if you prefer, or if your eyesight is not as good anymore, but that is completely up to you, of course. The other thing is that by default in Eagle, the vias are not covered, meaning that you will not have a silk screen over top of it. Now, this can be useful for debugging because you can use them as probe point, but I feel like it does not look as nice as covered vias. The way you can change this is going into Design Rule Check, under Masks. By default, the limit here is set to 0, meaning everything above 0, all hole sizes above 0 millimeters will not have any solder mask over top of him, but by setting it to 0.5 millimeters, all of my vias will be covered, but the large ones that I'm using for my mounting holes, they will not be covered as they are above this limit. Now, if you have some vias now that you do want to have not covered, to be able to use them as test points, you can always go right-click, Properties, and then you can tick this stop pin, which will mean that there is no solder mask applied to this via. One last tip is if you go to View, Flip Board, you can look at the board from the bottom. As by default, you're always looking at it from the top, and if you have all of your components on the bottom, you might want to look at it from the other side. Just keep in mind which side you're looking at it, as it can get a bit confusing otherwise. Then once you have finished your PCB, you can head over to your board manufacturer like PCBWay, who has sponsored this video, and you can go ahead to PCB Instant Quote, enter all of your details. I'm just gonna put 50 by 50 for now, and click on Calculate, and as you can see, it is just $5 for 10 pieces, which is a great price. And if you enter my code link down below, then you will get $5 off of your first order, so this will be completely free. Now, one thing you might want to do is customize your solder mask down here, and also if you don't want them to add the PCB order number onto the PCB silk screen, make sure to check that. It does cost an extra $3, but I think it's worth it. Now, for this more complicated PCB, it is also a really good idea to order a stencil. This is basically a metal part that allows you to very easily apply solder paste to your PCB and make assembly just so much easier. You can work without it and just use a tiny syringe to apply the solder paste manually to every pad, but that is quite messy, big pain, especially with this many components. Now here you want to make sure to choose non-framework, as you are not working with a manufacturing plant. You don't need a big frame around it. That makes it more expensive and more difficult to work with. With non-framework, it will just be shipped as a flat thing and just the size that you need. Here on the stencil side, you want to choose which side it is on. For us here, it will be the bottom. And all the other things you can just leave by default. And as you can see, the stencil itself is not expensive either. It's just $10 and definitely worth the trouble that it saves. They do also offer assembly services, but for these kind of PCBs, it's not really worth it to get it assembled, as it is quite easy to do it yourself as well. Now, speaking of assembly, once you get your PCBs, you want to cross your fingers and assemble it to see if it works. And you can just put the stencil on, line it up nicely. I like to put some tape down so that it does not move. Apply some solder paste and use just a squeegee or something to apply it neatly everywhere. The kind of solder paste you use doesn't matter that much. I just like using one with a very low melting point, as that just makes it a lot easier to reflow solder. And I am also using ones with lead in it. Lead-free ones are, of course, best for the environment, better for your health, but they are a bit more difficult to solder. And for kind of like DIY projects like this, I feel like leaded solder paste still is perfectly fine. Now, one thing you want to make sure is that you don't lift up and put down your stencil too much, as that will kind of smear it around. And also around your like these small pads, you make sure that it's nicely pressed down and there is no extra solder paste. The thickness of the metal is just right, so that the amount of solder paste that you put on is the correct amount, or at least close to it. So if you kind of have it bulging up or something, then you will put too much solder paste, which will then probably cause bridging. After applying the solder paste, you can take that off, put on all of your components nice and neatly, make sure that they are the right way around, and just kind of lightly press down on them. To reflow, there are very many options. You can get reflow plates where you can put your PCB on that have a little heater that will heat it from the bottom. You can get reflow ovens that heat it nicely all around. Or if you're just starting out, you probably have like a heat gun lying around somewhere. Or you can get a very cheap reflow heat gun off of AliExpress or somewhere and use that. You want to make sure that you can regulate both the temperature and the speed of the air coming out, as you want not a lot of air, otherwise you will probably blow away your components, and you don't want too hot. Like many heat guns will go up to like 600 degrees Celsius, which is way too hot, and you will just damage your components. You just want to go a little bit above the melting point of your solder. I believe mine is around 180 degrees Celsius as the melting point for the solder, so I've set my heat gun to around 220 to 250 degrees Celsius. I'm also using a preheating element since I just recently got that, but this is completely optional. It just heats the PCB from the bottom as well and makes it so it's a bit easier to reflow solder. Once you get up to temperature, at first you will see the solder paste kind of get liquid. That's when the flux melts and it kind of flows all over the place. And then a little bit later, all the solder beads will melt and start pulling together, and then you can really see the solder mask in action, as it will make sure that all of the solder goes onto the pads and nothing is next to it. Now you do want to keep heating a little bit after that, so that all the solder can flow into the nicest spots and all of the components align themselves. It's actually really cool to see that if you have like a resistor or a diode slightly crooked on there, the solder will actually pull it nicely into shape, and that is the beauty of reflow soldering. Now, especially for the 3535 LEDs, they are quite a pain to solder, as you cannot see the pads very well and they are underneath the LEDs. To make matters worse, these LEDs are quite heat sensitive, so if you heat them a bit too much, they will break. And I've definitely broken quite a few of them using a more cheap heat gun. So you want to be patient with those. Don't set your heat gun too high, and after the solder has melted, keep heating for quite a bit, as otherwise you might have a short underneath. Then once all the SMD components are soldered, you can go ahead and put in any through-hole ones, solder in the shielding of the USB port. But before you plug it in, make sure to first have a visual inspection. Look at all the pads, especially around the microprocessor and the USB ports. If you see any bridging, use a soldering iron to kind of try to remove the bridging by just reheating the pads. In many cases, the solder will just flow to the pad and you will not have to do anything else. Otherwise, if you have just too much solder, you can use some solder wick to clean it up, and with that you should be able to remove any bridges that you can see. At this point, make sure to use a multimeter, check just VCC to ground. If there's any short, that's usually where the shorts are, as they are in many cases right next to each other. So if you have a short between VCC and ground, go over all of the pins of the microcontroller again, check whether some of them might be bridged. Otherwise, also go check at the USB port, they also can bridge sometimes. Lastly, I also like to check between data plus and minus of the USB port, as they are close together as well, and if they are shorted out, then it will obviously not work. If you no longer have a short between VCC and ground or between the data pins, it is safe to then go ahead, program your PCB and plug it in. The programming part I will cover in much greater detail in the video about the software, where I talk about the various options that you have for the firmware on these kind of boards. Now at this point you should have hopefully a working PCB, but
make sure to go check out all the keys if all of them work, and if some of them don't work, well, recheck your soldering. Sometimes you forget a point of solder, or otherwise just go in deeper. And if for some reason something is not connected, something is not working properly, don't beat yourself up about it. It's very natural. A lot of my PCBs have little wires soldered to the back of things that I forgot, things that I had to change. And the first revision of this one, I actually have an LED placed right here. And this is probably obvious to you. There's a USB port right here. And it is on the same side as this LED that I placed right here. And surprise, surprise, putting a USB port and an LED in the same space does not work. So that is why you can see that one of the LEDs is not lit up on my board, as luckily this was the second to last in the chain. So by just not populating that LED, the only one that was not working is the one coming after it. And all the other ones work fine. But live and learn. I have of course corrected it here for the files that I have linked down below. But this is another reason why I like working with PCBWay, as the PCBs are so cheap that it's not really that big of a deal if the first revision does not work out and you have to reorder them to get them to work properly.
So with that, we're at the end of this video. I really hope that this helped you out in designing your own keyboard PCBs. And if you have any more questions, leave them down below in the comments. Also, make sure you subscribe so you don't miss the future parts where I go over the hardware design and the software involved to make these keyboards work beautifully. With that said, thank you guys for watching, and I'll see you next time.